Hello, Blake, Daniel. It's good to see you guys yesterday and get a chance to talk a little bit while you were taking the test. I don't have it graded. I told you I wouldn't have it by today. Hopefully I'll have it by the end of this week and we'll be able to see just how you guys did. Congratulations are in order, Blake, and making a decision there to go to George Fox. I think that'll probably be a great fit for you. So I'm glad to know that you made a decision on that, and I told you in the text there are some good things about that. So that sounds great. All right, let's go ahead. Let's move into chapter 17. We're going to go with Green's theorem here. So this is 17.1. So first we need to kind of go over a little bit of ground rules that'll help us understand what Green's theorem is talking about and what's going on. So first, notationally speaking, this notation here is essentially the partial of a domain here. So it's kind of like the partial derivative of a domain. What we mean by that is a counterclockwise complete circuit of the closed boundary curve C of a given area or domain D. So that's what we're talking about there when we consider that. So it's a counter. So when we see that notation, that partial with D, we're talking about the complete counterclockwise circuit of the closed boundary curve C of a given area D. If you want to, you can see a good illustration of that in your book. If you turn, I would say it's on page 1003, but Daniel, I know your page numbers I think are different. But it's in figure 1. If you take a look there, figure 1 there on 17.1, you'll see it illustrated well. Okay, the next thing to note, and this is kind of going back to a little bit of notation stuff. So if we've got a vector field and we say its components are function 1 and function 2, they're function 1 for the, you can think of it as field function 1 for the x, field function 2 for the y. Then if I want to take the integral over a parameterized curve C of their vector field dot ds, another way to express that is the integral of the curve C of our x component dx plus our y component dy, but we do have to consider that our dx is the derivative of our parameterized x component dt, and our dy is the derivative of the parameterized y component dt when we take a look at that. So we do need to remember that that's what we're actually getting there. And that becomes our, if you notice, that becomes our dot product there that we can see there, because this derivative here would be the derivative of the x component, which we would have here, the dx times the x parameterized. And so we see how we get our dot product there. It's just a different way of notating it. But this notation becomes helpful when we look at Green's theorem. Whereas we've used this most typically, we're probably going to use this now a lot more when we see Green's theorem in action. So let's look at Green's theorem. Green's theorem basically, as we're going to see, I'll illustrate with our first problem, becomes a nice tool to do things easier in certain circumstances. So what it says is if we want to take the line integral, notice the line is this is that when it's a closed curve. So we've got that closed curve there. That's what that symbol there denotes, remember, is a closed curve. And it's around some given domain, around some given area there of this vector field. So we've got this vector field there. That's going to be equal to the double integral over the domain of the partial of the y component with respect to x minus the partial of the x component with respect to the y dA. The advantage that this has here is this eliminates the parameterization piece. So notice as you take a look here, we see no parameterization pieces need occur. And we'll see how that becomes a real advantage at times. Okay, so let's take a look at how it becomes an advantage. Let's look specifically at number 2. So number 2 gives us the following vector field, y plus the sine of x squared, and then for the x component, and then x squared plus e to the y squared for the y component. And it gives us the curve. It's the circle centered at the origin there. X squared plus y squared equals 16. So that circle centered on the origin with radius 4. So, and it wants us to evaluate that integral of that curve over that vector field. Now notice, in order to do it, if I was going to do it the classic way, now what 2 does is 2 actually asks you which way is easier, so I'll show you how you can see that. So let's say I was going to do it the classic way. The classic way to do this would require me to parameterize this curve. So parameterizing the curve, I know that would be 4 cosine t, 4 sine t. And then I could do either my dot product here, or I could use this form here. I'm going to use this form here, which is just the dot product spelled out here. So here it is without greens. Notice, without greens, I would have my parameterization. My parameterization here, notice, t goes from 0 to 2 pi. So those would be my limits there. But notice what I would have here. What I would have is I would have my x component, that's my 4 cosine t here, times my derivative with respect to x, which in this case here, my x prime here is going to be the derivative of that. I said that wrong. It's the x component of my vector field, which in this case is this right here, with these substituted in for x and y. So there's the x component of my vector field. In for y goes 4 sine t plus the sine, and in for x goes 4 cosine t, and that needs to be squared, and that whole thing needs to be multiplied by my x prime, that's the derivative of this, so that would be negative 4 sine t plus, and now I have to go ahead and fill in this here, so for my x I go 4 cosine t, that's all squared, the whole 4 cosine t, and then it's added to e, and then the y, what goes in for the y is the 4 sine t, that is squared right there, and that's multiplied by the derivative of this y component here, dt. Well, right here I can tell you I did evaluate it. If you plug this big old mess in your calculator, I did set it up correctly, you will get the correct answer. But for obvious reasons, this is not going to be something that we have any good, easy way to go ahead and integrate this. Okay, this is just going to be a great big mess that we're not going to have any good way to integrate. So, Green's theorem will allow us an easier way to integrate this because it can eliminate that having to parameterize things, which gets real messy real quick. So let's look at what happens with Green's theorem. So with Green's theorem, what we're going to go ahead and do, and we're just applying this in here. So this was our initial situation. We are going to go over the double integral, and now I can take the partial of my y component with respect to x. So that's this. Take the y component, differentiate with respect to x. This just becomes a constant. You just get 2x minus the derivative of the x component with respect to y. So that would just be 1. And then that is over the area. Now, here, the area that we would have to consider, this is where it can get a little bit challenging, just how we want to go over that particular area there. But in this case here, what I can actually do is, because I know that this curve is the oriented curve around the origin, centered around the origin, I can actually do this fairly quickly because I recognize it's going to be of this form here. Well, by looking at this, what I'm going to see there is, knowing my symmetry of this function here, that the fact that it's an odd function, what's going to happen is if I go and integrate it over that area, I'm going to get equal portions, positive and negative, so it's just going to be 0 when I go to do that, since that's an odd function there over that particular area. And this one here, I should recognize that is actually the formula that gives me the area. the double integral of a domain, my function being 1 over dA, that just gives me the area. Well, I know what the area of a circle centered on the origin is with radius 4. It's pi r squared, or pi times 4 squared. So this is just going to be 0 minus 16 pi, or negative 16 pi. So it becomes very quick and simple with that. Now, most of the time, we're not going to evaluate these integrals in this fashion. We're going to actually express them differently as we go to integrate and do it that way. But that's just a quick example of how we can do it. And that one happens to be pretty easy to do just by inspection. All right, let's go look at some now where we don't just go ahead and do it by inspection. So here's number 4. So number 4, we are writing it in the form, in this form here that we said we would look at quite a bit, as opposed to our form like this of the that we're used to seeing of the vector dot product. This is where our dot product has essentially already happened. And we know our curve here in this case that we're given is the path around a triangle going from the vertices 0, 0 to 1, 0 to 1, 1, and then back to 0, 0. So it's that path going around there. Well, if we take a look at that, what that shape looks like, you can take a look in your book. I think there's a picture of it there. We're going to make it a vertically simple region. If we look at that, it becomes a vertically simple region, and I guess there isn't a picture in your book. But picturing that triangle there becomes a vertically simple region where it's going from x values of 0 to 1, and the y values are going between the x-axis and the line y equals x. So I can set this up to be as follows. So first thing that I do is, I know this will be of the form, I take the derivative of the y component, which is this, with respect to x, and that's just 0, minus the derivative of the x component with respect to y. That just becomes minus, it comes e to the 2x plus y. Now I have to worry about my limits of integration, so it's actually going to be of that form there. So my limits of integration, my x limits go from 0 to 1, and my y limits go between 0 and the line y equals x. So I have that dy dx, like we've done quite a bit before and have looked at it. So now let's go ahead. Now it's just a matter of evaluation, just to remind you how that works. So I go 0 to 1. When I integrate this here with respect to y, looks like I just go ahead and I get the exact same thing, negative e to the 2x plus y, evaluated from 0 to x. So substituting the x in there, and I get the integral 0 to 1 of e to the 3x. And then when I substitute 0 in for y, I get that to be minus. So it's minus and negative, so it becomes plus e to the 2x dx. Now integrating with respect to x, I get the following. This should be stuff we're fairly familiar with doing. Substituting in 1 and then 0. Substituting in 1, I get negative 1/3 e cubed plus 1/2 e squared minus, and then I would get negative 1/3 plus 1/2. So this becomes 1/6. So it looks like I've got, if I rearrange it, so I go positive 1 first, I have 1/2 e squared minus 1/3 e cubed minus 1/6. And there's our answer. All right, let's look at one more. This one's a little bit different. So this one, we actually do have it of the form of our dot product here of our vector field. And we're given our vector field, x component x plus y, y component x squared minus y. And we know that our curve C is going to be the region or the curve around this region here, trapped between these two curves, the y equals x squared and y equals square root of x. So if I look at that, that's a picture of the region we're talking about right there. Okay, so I'm actually going, we know it's oriented counterclockwise so we know we're going in this direction like this. But notice it's another one that's vertically simple. X goes from 0 to 1, and we've got the y values trapped between x squared and square root of x. So now we can set up our formula here. So first off, we're going to do our partials, your Green's theorem. So we have the double integral over our domain D, and we've got our derivative with respect to x of the y term, that's 2x, minus derivative with respect to y here of the x is just 1. So now this is going to be 0 to 1, x squared to radical x of 2x minus 1 dy dx. I think you guys know what to do from here. I did go ahead and integrated with respect to y, and then substituted in my x values there, and got to this. And I think you know how to finish that one off. I don't think I need to go through. Plus, I'm out of room on my paper. I think you guys can evaluate that. And you will get an answer of negative 1/30 when you do bring it to conclusion. Okay, homework is going to be 17.1, 1 through 9, all of those. And go ahead and have at it. And on number 1, you are supposed to do it both ways. The difference is, unlike where I did number 2, when you get something horrible that can't be integrated when you don't use Green's theorem, on number 1 you will get something that can be integrated. But you need to see how you can do it both ways. All right, hope things are going well, and see you in tomorrow's video.